Hello everyone, this is Group 1 from Division I and our topic is cache memory. So what is cache memory? Before moving to what is cache memory, let us discuss the purpose of introducing it. So in any device, we have the processor, the RAM and an SSD or a hard disk. So data flows basically occurs from the SSD to RAM and then from RAM to the processor. But the rate of flow of the data is much slower from SSD to RAM than from the RAM to the processor. So therefore, in this situation, the processor requires a lot of time to access the data from the SSD. So here comes the part of cache memory. As it has less storage capacity, it can transfer data as much at much higher speed, and therefore it solves the problem of the access time, as it reduces the access time for the processor to access the data from the SSD. This is the basic memory hierarchy, and here is the cache memory. So as you can see here, cache memory is a part of CPU and it is inbuilt in the CPU, so you can't change the size of cache memory. And so a cache memory is also a type of SRAM, which is static random access memory. So what is static random access memory? So it is a type of RAM which is made up of latching circuitry or flip-flops, which individually stores each bit. SRAM is a type of volatile memory, which means the data is lost as soon as the device is switched off. The term SRAM is different from DRAM, which is dynamic random access memory, as DRAM requires refreshment of its memory periodically. SRAM can store the data permanently until the power is cut off. Also, the SRAM is much more expensive than DRAM because of the silicon area it uses, so which increases the cost. Also, SRAM is much faster than DRAM. So cache memory is a type of high-speed memory, which is smaller in size as compared to other memories, and it stores the frequently used main memory locations. For example, if we use WhatsApp daily, so when we open WhatsApp, it opens quickly as compared to other apps, and the data can be accessed easily. This is because cache stores the data to access the WhatsApp program uh, for the processor, which reduces the time. Also, cache memory acts as a buffer between the processor and the hard disk or the SSD to decrease the access time of the processor. Also, cache is much more costlier than other memories, but it is cheaper than CPU register as a matter of speed and volume. So this is a basic example of a processor having cache memory. So this one is a processor from Intel i5 12 Gen H series 1. So the L1 cache here it is 1.1 MB, L2 is 9 MB, and L3 is 18 MB. So the second one is of i7 12 Gen H series 1. It is much costlier processor because of many reasons. One of the main reason is the size of cache memory. As you can see in most of the cases, the cache memory capacity is much larger than the earlier one.
Now let us see different level of cache memory. The first level of cache memory is known as level 1 cache or L1 cache. So in this level 1 cache, tin amount of memory is integrated inside the CPU itself, and all the cores inside CPU have their individual level 1 cache. So as this level 1 cache integrated inside the CPU, so they can operate at the same speed of the CPU. And that is the reason level 1 cache is fastest among all cache. Now the typical memory size of level 1 cache is 2 KB up to the 64 KB. Now inside this level 1 cache, there is two kind of cache. The one is instruction cache and the second is data cache. So the instruction cache store all instruction which are required by CPU and the data. Cache store the data which is required by CPU. Now let us see second level of cache. So this cache is known as either level 2 cache or L2 cache. Now this level 2 cache could be either inside the CPU or it could be outside the CPU. Now this level 2 cache could be separated for all the cores or it could be shared between all cores of CPU. So if this level 2 cache is outside the CPU, then it is connected with a very high speed bus with the CPU. So the memory size of this level 2 cache is in the range of 256 KB to 512 KB. But in terms of speed, they are slower than L1 cache. Now the third kind of cache is known as level 3 cache. So all the processor do not have this level 3 cache, but some higher end processor have this level 3 cache. And this level 3 cache is used to enhance the performance of level 1 and level 2 cache. So now this level 3 cache is shared among all cores and it is outside the CPU. The memory size of this level 3 cache is a range of 1 MB up to 8 MB for high-end processor. But it is slower than L1 and L2 cache. But still it is faster than random access memory or RAM.
Now let us see the process flow for accessing cache memory. So whenever the CPU needs the data, then first of all, it will look inside the L1 cache. So if the memory is not found inside the L1 cache, it will look inside the L2 cache. And if the data is not found inside the L2 cache, it will look inside the L3 cache. So moving forward, let us clear some concepts about cache memory. So if the data inside the cache memory is available, then it is known as cache hit. And if the data is not unavailable inside the cache memory, then it is known as cache miss. Okay. So moving towards topic, suppose the data is not available inside the L3 cache also, then the CPU will look inside the RAM, that is random access memory. Still, if it doesn't find any data inside the RAM, then it will get the data from the hard disk. So whenever you are starting your computer for the first time, or you are opening any application for the first time in your computer, then that data will not be available inside the cache memory or in the RAM. At that time, CPU will get the data from the hard disk drive. And once the application is open, then after it requires some data that CPU will get either from a RAM or from cache memory. Now you may ask, as the cache memory is so fast, then why is the size of the cache memory only in megabytes, right? The reason behind that is the cache memory is much more costlier than any other memory. That's the reason that you will find a few megabytes of cache memory inside the CPU. So whenever you are buying a desktop or a laptop for yourself, don't only look at the random access memory, but also look at how much cache memory does that CPU got, because that cache memory decide the overall performance of the processor. The same thing is applicable for the smartphone processor as well.
Hi guys, this is Dheeraj here and I am here with the topic cache mapping. Cache mapping is a process that determines how cache memory is organized and how it maps to the main memory. To explain it in simple words, I'll tell you that we have gotten the idea that cache memory is too fast and efficient. Now to put this to our advantage, what we do is transfer the data from the main memory to this particular cache memory. The process of transferring this data from the main memory to cache memory is basically what is mapping. Linking the data and storing it in particular lines in the cache memory is cache mapping. Now here's how the transfer works in this particular diagram, which I'll be explaining in the further slides. So basically there are three types of cache mapping techniques. First to be called direct mapping, second is fully associative mapping, and the third one is called k-weighted associative mapping. I'll be explaining the direct mapping one here. In direct mapping, each memory block is assigned to a fixed location in the cache memory based on its memory address. This means that whenever a memory block is requested, the cache controller checks if the memory block is present in the cache memory by checking its location in the cache. I'll be explaining this in detail in a few examples which I will be taking further. Now let's take an example here with the main memory having some blocks and words in it. Blocks numbered from B0, B1, B2 till B31 and words mainly from W0 to 128. And let's see cache memory to the side of it. Cache memory contains lines as the main memory contains blocks numbered from line 0, line 1, line 2 and line 3. In this particular example we have took 4 lines. Now we have a formula in direct mapping k mod n. This formula basically tells us which block will go in which line, where k is the block number and n is the line number. Now let's take an example here. B0 mod 4. That is the block 0 and the total number of lines we have is 4. So in which will it go? That is B0 mod 4. Since the remainder becomes 0, the block goes in L0 and so on. Now next is accessing memory. For accessing some random word, we generate a physical address in the memory. This physical address basically contains of two parts. First is block number and the second one is block offset. Now to better understand accessing memory, we take an example here, the previous example, which had 128 words, right? We can represent this 128 words in the way 2 to the power 7 equals to 128. That is the required bits becomes 7. Now we have to divide this 7 into two parts, the block number and the block offset. Now talking about block offset, we get that there are 4 words in each block. So that 2 to the power 2 is 4. So the required bits become 2 and we put the 2 in the block offset. Now the remaining bits are 5 which become in the block number. Now let's take an example here that the CPU has generated some random address. We'll divide it into 5 bits 0, 0, 0, 1, 0 and the 2 bits 1, 0. Now what is this basically 0, 0, 0, 1, 0? This is 2, right? And what is this 1, 0? This is also 2. Now the block offset tells us basically which word in the block, which becomes the second word. And what is the block number? That is 0, 0, 0, 1, 0, again the 2, right? So block number 2 and word number 2. So it is basically the block number 2. This is block 2 and W0, W1, W2. This is the word we were searching for, word number 10. Now, once we have brought a word or block from main memory to cache memory, accessing the word or block has a different approach. Now, in this one, we divide the physical address in three parts. The block offset remains the same, but the block number is now divided into line number and tag. Now, what is tag? Tag basically tells us the block number or word number we are searching for. Now, let's see the redistribution of the bits in this one. The block offset has 2 bits as the earlier one had, it remains the same. But now the line number, we have 4 lines here which can be represented as 2 to the power 4. So this becomes 2 bits and the remaining 3 bits are here in the tag. Now let's take an example with the same. Let's say we took a tag 010 of 3 bits. Line number is, let's say, 00 and the block offset. Now the block offset has 2 bits which we can write as and represented it as 00, 01, 10 and 11. Now let's see this first one. When we convert this into decimal, what does it become? 0, 1, 2, 3, 4, 5. That is 2 to the power 5, which becomes 32. Now 32 becomes the word number 32 in this one. That is, and so on, word number 32, word number 33, word number 34, and word number 35. Now, we have seen this earlier that the block number 8 contained this word. Word number 32, word number 33, word number 34, and word number 35 was in block number 8. And which line has block number 8? It was the line 0, as we have said earlier. With this, we conclude direct mapping.
Associative mapping is a memory mapping technique used to map main memory addresses to cache memory addresses. It is also known as content addressable memory or associative memory. In this technique, each block of main memory is mapped to any cache memory block that has free space. Associative mapping is commonly used in high performance computing systems such as supercomputers and high-end servers. The CAM compares the memory addresses to be accessed with all the memory addresses stored in the cache simultaneously. If a match is found, the requested data is retrieved from the cache memory block that corresponds to the matched address. Assuming there are 4 lines in the cache, suppose the generated physical address is of 8 bits and the least significant 2 bits of the physical address is the offset. Therefore, the remaining 6 bits are going to be used as block numbers. In associative mapping, block numbers are used as tag bits, so all the 4 lines are going to be connected to a 6-bit comparator each, to which the tag bits of the physical address will be attached parallelly. Now the outputs of the comparator will be given as inputs accordingly so that it can indicate the cache hit if any of the lines have the required block. Set associative mapping is a memory mapping technique used to map main memory addresses to cache memory addresses. It is a compromise between the flexibility of associative mapping and the simplicity of direct mapping. In set associative mapping, the cache is divided into multiple sets, each containing a fixed number of cache memory block. Each main memory block can be mapped to any of the cache memory blocks in the set. If the requested data is not found in the cache, a cache miss occurs. In this case, the cache controller determines which cache block is the set to replace with the new data. This decision is usually based on a replacement policy such as least recently used LRU, which replaces the cache block that has been least recently used.
Now we will see the advantages of cache memory. First is faster access. Cache memory is much faster than main memory as it is located closer to the CPU. This results in faster access times and improve overall system performance. Second is reduced traffic. By storing frequently accessed data and instruction in cache memory, the system can reduce the amount of traffic on main memory, freeing up bandwidth for other operations. Third is lower latency. Cache memory has lower latency compared to main memory, which means that it can deliver data to the CPU much more quickly. Then disadvantage of cache memory, limited size. Cache memory is more expensive and smaller than main memory, which limits its size. This means that only a small portion of the data and instruction can be stored in cache memory at any given time. Then second is cache misses. If the data or instruction that the CPU needs are not present in cache memory, a cache miss occurs and the CPU must fetch the data from main memory. This can result in a delay and lower performance. Third is complexity. The caching algorithms used by the system can be complex and require careful tuning to achieve optimal performance.